Hello again, welcome back. What I want to do is continue where we left off in regards to the work examples number one, okay? And you have work example number two. Now, my calculations here for this is that number there could be incorrect, but do the calculation for yourself for me, please, and be sure that you've arrived at the correct solution. Now, look and use the electrical principles books that you have to make sure you're calculating the speed, okay, because there's a little bit of transposition to be done in regards to the formula, okay, but you should be able to do it by now, and some of you are quite good at it. Excuse me, I've got a cold and it's winter. Right, just to recap, I'm just going to go back a bit. Let me just go back up a bit quickly. Okay, just to recap, unit 2 engineering science, okay, level 4, so you'll be doing at agency level. And again, I state that some work might be applicable to ONC, okay, or your T level work now, okay. Just recapping, so nothing natural you haven't seen here already, okay. I'm not going to take too long on it. Terminology used, etc. Okay. Losses, okay. And we're at our work example. So what I want to do here is to have a look at work example number 2. Now, a DC motor runs at 600 revs per minute and is supplied at 300 volts. Calculate the approximate speed when the supply is reduced to 200 volts and the flux is reduced by 30%. Solution. Now, N1 equals 600 over V1 over K theta equals 300 over K theta 1. So we know that here we have to transpose. So you'll see that we're transposing for K theta 1. We have N1 equals 600 and we have the 600 here. So we have done a simple transposition here, okay, to find K theta 1, which equals 300 over 600. Now, if we're going to equal 600, so what does that actually come out to? Let's have a look. Now, N2 equals V2, which is the 200 volts, over K theta 1 times 0.7. So, if we take this here, I make that 0.5, okay, times 0.7, and remember we've been given 0.7 Now I have a little question here. 0.7, where did the 0.7 come from? Now that's something that you will need to look into yourself and be sure that you understand the concept of it. Okay. We know K theta 1 is here. We know the 300 comes from here, and we know 600 comes from here. Okay. Okay, but I won't go into much detail for you. All I'm going to do is try to give you alternative options and different ways of looking at it, so you arrive at a solution that accommodates yourself. Okay. Now you need to know where this 0.7 comes from. What gave us 0.7? Got you. The 0.7, we've reduced the flux by 30%, so we've only got 70% of the flux present. The 0.7, comes from when we divide 100 by 70 by 100. Okay, gives us 0.7. So we now know where the 0.7 comes from. The 0.7 is the remainder of your 30%. So what we've done here is we've divided, because it's being reduced by 30%, that means that the motor is only the flux density is only at 70%. And we need to convert that to a decimal, so we bring it to 0.7. 70% divided by 100 is 0.7, okay? And that's where we get a 0.7 from. That answer there is correct at 571 revs per minute. As I've done the calculations myself, I know it is correct, okay? Okay, let's move on a bit more now. Motor field windings and configurations. Motor field windings, configurations. Now, what exactly does that mean? There are various ways of arranging the field windings and armature, but the two most common ways are in series and shunt, and a combination called compound. You need to study this carefully. Now, series motors. In this case, the field winding is in series with the armature. The same current flows through the armature and the field windings. The mechanical power of any rotor is P equals 2 phi nt. P equals 2 phi nt. 2 phi, okay, 2 pi nt. Sorry, excuse me. Equals 2 pi nt. The electric power of any rotor is ideally P equals EA times IA. Equating and rearranging, we see that T equals EA IA over 2 pi n. If the electric power is constant, EA, IA are constant, so T equals constant over n, whatever the constant is. This means that for a constant electrical power, the speed would increase as the load is removed, and decrease as the load increases, as shown by the graph. Disadvantage: at low torque, no load condition, the motor is liable to overspeed and become damage, burnout. At low speed, there is a high torque starting torque, which is ideal for servo applications. Excuse me. So let's see how we can apply this. Okay. Work example number 3. A series wound motor produces 30 kilowatts of mechanical power and is connected to a 250 volt supply. The motor runs at 800 revs per minute when on the load. The load is reduced to 200 Newton meters and a resistance of 0.5 ohms is connected in series with the motor. Assuming no energy losses, calculate the speed. Now we're assuming no energy losses, but you will always have energy losses in any motor that you have, okay? The idea here is to make the motor more efficient and ensure that it remains and contains its efficiency. Solution. Initial condition, motor current I equals P over V equals 30,000 over 250 volts equals 120 amps. That is correct. We know that to be the case, but do the calculation for yourself. So I equals P over V. That's equal to 120 amps. Excuse me. Now mechanical power equals 2 pi nt over 60 equals 30,000 watts. Now here we were calculating it in the current. Here we are calculating the mechanical power. Which equals 30,000 watts. Okay. Now T is the torque equals 30,000 times 60 over 2 pi times 800. And we know this comes from this. We know 60 cycles per second, and we're looking at 2 pi times 800. Okay, now when you actually begin to apply this, let me see if this works out. I'm just looking for my pi function on my calculator. Just bear with me for a moment while I find it. Okay, yes, got it. Okay. Times. So I'm just looking at how calculation of this can work out. Okay, for myself. Okay. Excuse me. Right, this has worked correctly, so I know it's correct, okay? And that is correct. I'm happy with this calculation here, okay? 358 Newton meters. T equals K1 theta IA. Since flux is proportional to current, and the field current is the armature current, then T equals K1A squared. So we're transposing for K in this case, aren't we? So here we're transposing for K, so we have to transpose for K. We look at it in a different way for a moment. Look at it from this angle. You would 1 second. Okay, how excuse me, sorry about the noise. I'm just trying to shift some papers here so I could get to something to work on. Oops, sorry. Oh. Right. I'm not going to remove any mistakes I've made or any errors I've made here. Simply because I think that making errors is all part of making a video. And although I would like my videos to be perfect, there's no such thing as absolute perfection. But you can try. Excuse me. Okay. Right. Oh, sorry. Okay. Pardon me. So here we have 358, and we know that came from Newton meters, equals K times 120 squared. Okay, K. Now, the interesting thing is that we have to transpose for K. Okay. And K times 120 squared. But we need to transpose for K, so normally I would just multiply both sides by K, okay? Both sides will then, K, that side will not multiply, but I'm not going to go for all that. I'm just going to go straight into it because you should know how to get to this already yourselves, okay? So transposing will give me K equals 358 times 120 squared, which equals times 120. Okay, it's given here not k equals 0.02486. Now make sure you understand how they have arrived at that. Because I have to admit here, I'm having a little bit of problem figuring out how he arrived at 0.02486. Maybe I'll look at it from a different perspective. Yeah, let me look at it from a different perspective for a moment. Yeah, k is going to equal 120 squared over 358. Let's try that. See if I go with that and see what it gives me. No, that won't give me that either. Okay, how did you get k? Okay, right, just work on getting k. Make sure you understand how he got k. Okay? Well, I have to admit here that I haven't worked these out prior to putting it online. I felt it's important that we look at it from both our perspectives. Huh? Right, what am I doing? What am I going on? I know what he did. Okay, I can see. Let me just try and see if this has what come out. How I think it should come out. It's yeah, it's okay. I've written it around a different way. And let me just try a different way now, my own way, a different approach. Well, all I'm looking at is finding a different approach to arriving at this solution. Okay, basically that's what I'm looking for overall. Um, so got it. Okay, found it. Okay, so flip that over. Excuse me. K equals 358 over 120 squared, which equals to 358 over 14400, okay, which then equals 0.024886. Okay, yes, okay. So my calculator is giving me some jib. Okay. Now I'm happy with that result. Okay. So for T, now you no final condition, use the same value of K. Okay. T equals 200 equals 0.02486 times IA in the armature squared. IA equals now 89.7 amps input power. Excuse me. 250 times 89.7 equals 22.23 watts. In short term, 22.4 kilowatts. Loss in 0.5 ohms resistance is IA squared times R equals 89.7 squared times 0.5 equals 4 kilowatts. Useful power, sorry about that. Weird things happening. Okay. Useful power, 22 kilowatts. Coming down to 18 kilowatts. Okay. Now again, this is just me going over this briefly at your level. You should be familiar with this. Now you need to write this work out yourself. You need to write it out and do the calculation for yourself. Do not try to do the calculation on here or assume that the answers are correct. It's not. Okay. Now this is Motor Principles 4, Session 4, I should say. Okay. And here we have some self-assessment for you to go through yourselves. Okay. And we would look at that. Now what happens here is that I'm going to see if I can put this a different way and get back to you on this. Okay. Let me just do some groundwork myself. I'll come back to you. Right, that's going to be it for now. I'm not going to edit out my errors or my mistakes. I want to show you that errors can be made and that there's nothing wrong in being adventurous. Okay, thank you for your time. Have a good day. Now I will continue with self-assessment exercise number 1 and let's see where we go from there. Thank you. Bye bye.